Hello, and welcome to today's webcast, Quality and Process for Academics. My name is Pawnee Allen, and I will be hosting today's webcast. We would like to answer questions that arise during the broadcast, so please use the chat panels to submit your question at any time. However, we will wait until the end of the presentation to address your questions. Let's meet our presenter, Kevin Potzner. He's an academic ambassador with JUMP. JUMP is a business unit of SAS, specializing in desktop software for dynamic data visualization and analysis. Now we invite you to sit back and relax, and we'll go ahead and get started.
Okay, thank you very much, Pawnee, for setting that up. Welcome to today's webinar. Very excited about this one for a few reasons. Topics in quality control is very big in industry right now, and quite a bit of exciting things are happening. I've gotten the chance to spend a good 20-odd years working on Six Sigma and other quality problems. And so I have a lot of experience in a variety of industries, and I happen to think it's one of JUMP's great platforms is what you can do in quality control applications. So a few topics that we're going to do today is one of the most popular ones is control charts. So I'm going to show you a bunch of different control chart options. Hold on one moment, I have a little issue with my slide moving. Oh, there we go. We're, of course, going to look at capability analysis, another big tool that folks out in the industry are using in quality applications. I'm also going to show you two other tools that are used quite a bit, and they relate a lot to capability analysis. It's called prediction intervals and tolerance intervals. Those are actually getting a tremendous amount of use right now, sort of a way to estimate how a process is doing in terms of where you land relative to specifications. It's kind of similar to capability analysis. I'm going to show this fun little tool in JUMP where you can actually do a little animation when you run a capability analysis. And this is useful not only for the purpose of analyzing, but I really think it's a great teaching tool. And when I get to it, you'll see how it's a really great way to explain to the students what's happening for different levels of capability and different levels of a process condition. We're also going to show a tool, I like this one quite a bit, is where we could do a capability analysis on many variables. And instead of sort of just looking at individual capability analysis and trying to compare them, JUMP has this platform that actually creates a bunch of output, and these are just two samples of output you're going to see, which try to evaluate the capability in that multi-variable sense so you can kind of compare and contrast all of them. We're going to look at doing some measurement system studies. You might know them as gauge R&R studies. We're going to do a measurement system study for continuous variables. And then we'll also look at doing what's called an attribute agreement analysis, where you look to see if appraisers are correctly or incorrectly rating the condition of something they're evaluating. And if we have time, I'm hoping we do, I'm going to give you a little peek at design and analysis of experiments for a couple of reasons. I think this is a great platform in JUMP. And if you teach a quality control course, it's pretty typical that you may spend a week or two introducing the students to design of experiments. For example, if you're using Montgomery's quality control book, he has a few chapters on full and factorial design. I don't know if I'm going to get to this. It depends how the pace goes, but if so, I'm hoping to do so because it's a really great platform in JUMP, and I'd love to show it to you. Okay. Right here. Okay, so I'm just open up a JUMP file. Okay. Okay, so this happens to be a sort of a process that's being measured, and the key variable is this diameter. And you can see that we're measuring it across different days. We've got different operators, machines, and phases. I'm not going to be using all of these variables, but I'm going to be using a few. But the key one, of course, is diameter. So, and this is what I'm about to say is true in many different analyses in JUMP. You can get to it through various platforms. And I like that because you might be doing one analysis and you think, hey, this is a great place to, say, run another analysis, and you can get to it from there or get to it from another platform. So what I'm first going to do is I'm going to start off with a tool in JUMP called distribution, which is just the way you do a simple summary graphically and numerically of a variable. So I'm going to put in diameter. And if for those of you who aren't familiar with JUMP, you'll see how easy it is. It's just clicking on variables, dragging them into different roles, hitting OK or run, and the analysis runs. So it's really quick to get up to speed really fast with JUMP. As you see, so I'll click, point and click, drag and drop. Okay, so I'm going to run this distribution analysis on this variable diameter. Yeah. Now I've got two screens going, so I have to keep on dragging up the output. So so bear with me. That's kind of what I'm doing. So as you see me kind of pull things from the bottom of the screen because they're on a different screen. Okay, so this analysis that gets done, this distribution analysis, JUMP recognizes, hey, that's a continuous variable, so you must want a histogram, maybe a box plot, a bunch of summary statistics, and you can change a lot of those summary statistics if you want, but there's a default set. But the reason why I'm starting with this is this might be the way you just start with an analysis, right? Just let me look at the data and see what I've got. And you might think, hey, now would be maybe a good place to do a capability analysis. Now, there's other places, as I said, to do this in JUMP, but you can do this right from here. Okay, so if I hit the red triangle, and for those not familiar with JUMP, as you run different analyses, you'll see these little red triangles everywhere. And when you click on them, that's where various options pop up related to that particular platform. So in the distribution analysis, these are all sort of the sub analyses I can run after running the distribution analysis. And as we go to different platforms, you'll see that the options under there, of course, are going to be different. Okay, so you'll notice that one of the options here down towards the bottom is to run a capability analysis. So I'm going to click on that. And of course, to run a capability analysis, you need to know what the specifications are. So first thing JUMP is going to ask you is, well, why don't you go ahead and tell me the lower and upper spec limit and the target. And so for this process, it's lower spec of 3, upper spec of 5, and a target of 4. And you can see that I can pick different distributions here. The default is normal, and if you take a peek at the histogram, that seems very reasonable to do. But if you had a reason to use a different distribution, you can select it from that drop-down. And of course, there's other options in terms of how you want to estimate variation, and if you're going to do short-term moving ranges and all of that, you can specify that here. I'm going to leave it as the default of just long-term and hit OK. And when I do that, what gets added to this distribution output is, over here on the right, is a capability analysis. Now, this is a little bit of an abbreviated version. When we run the true capability analysis platform, we get quite a bit more information. But for this first one, this is a quick little output. So again, you get various values with classic capability metrics, percent out of spec, CPK, all of that content. But the reason why I went here first is what I want to show you is this little neat tool that I mentioned, which is called capability animation. So when you run that, up pops this little interactive window. Now again, I think this is great for analyzing, but I think it's awesome for teaching. Because when you're teaching students about a tool, say like capability analysis, the whole idea is what happens when things change. Okay? So I can slide over this blue distribution, the shaded distribution, and say, for example, put it right on, there's no mean shift. I'm getting it pretty close there to 0 mean shift. And I can look at sort of the capability metrics, right? Parts per million out of spec, CP, CPK. And so what do you do when you teach? Well, you want to explain to students, well, as the distribution shifts away from that target, you'll see the capability metrics change, right? And more lands out of spec, and again, going the other way, more goes out of spec this way, and then you can see that if I drop that right in the center of those spec limits, where it's right on that target, you'll see that the capability metrics will be the best. So I think this is a great teaching tool, both to do in the classroom and for the students to play around with to learn, well, what is capability and what happens as a distribution shifts around and how do those metrics change? So I'm going to close this up. And again, this is just one way to get to a capability analysis. I'm going to show you a different way in a moment. Okay. But before I do that, let me show you some control charts that you can do with this data here. Okay, so again, the variable we're analyzing is diameter. Right? So if we go under the Analyze menu, so we've got this Quality and Process Capability Platform. And there's actually a couple ways you can even make control charts. One is this control chart builder, and the other is selecting the particular chart under the control chart menu. So I'm going to start with this. So let's say to start this, I'm going to do an individual and moving range chart. Okay? And again, platform in Jump opens up sort of this dialog box, and then we just cast the different variables into the different roles. So I'm going to put diameter. I can drag it right over there. And again, I can come over here and select, is it going to do a moving range? Is it going to use the median of the moving range? I can choose what is that moving range stand. I'm just going to leave it as the default. Okay. And hit OK. And up pops the classic individual and moving range chart put on top of each other. Now, a nice thing that you can do in Jump, and you can do this in almost every piece of output, is you'll see these little triangles over here, these little gray triangles. Well, that allows me sort of to collapse or expand output. So I think it's nice because it can keep your screen clean as you're looking at things. But when it comes to teaching, it's nice because if you want your students to just focus on a specific piece of output, you can sort of collapse all of it and just keep them focused on specific output, and then open up other pieces of output as it becomes relevant in your teaching and discussions. And like I shared, in the distribution platform, when you go to the red triangle, notice you'll see a whole bunch of selections here that are related to what might I do to this individuals and moving range chart. Right? So there's, in addition to analyses, there's a lot of things like changing colors, line widths, a lot of things you can do sort of to change how the graphic is displayed. There's all the standard quality control tests to see if points are, whether it's falling outside the limit, there's a certain number of points in a row going up or down, all those classic standard ways to evaluate this control chart and do it more than just visually seeing. So again, if I go into moving range, whole set of options related to the moving range. Now I'm going to close this because I'm going to run, actually, I'm going to run it again. Right. Now you may have noticed that I have this column right here called phase. And I'm just going to scroll down so you can see it changes from 1, and then it goes to 2. Okay. So it's common that in a process, there might be distinct changes being made. And so when you make a control chart, we may want each of those phases looked at separately. And so I'm going to put this phase variable right in this spot phase, and you'll see what happens. Okay. So what you're going to get is a separate individual moving range chart for each of those phases. So in practice, this is commonly used, right? Because you're trying to show, hey, we're making changes to a process. We want to see how that improvement is playing itself out. But it's really great for teaching because now you can have different conditions. Maybe you want to illustrate the mean is at some level, and then phase 2, the mean's at a different level, or in phase 3, maybe the standard deviation changes. So when it comes to teaching, you could sort of create this data set to illustrate the kind of concepts or points you want to make about watching processes shift and change. So again, even though it's used in practice, it's a great tool for that. I think it's a great tool for teaching because I always found the best way to learn is to compare and contrast things as they change. And so I think students would kind of appreciate watching how things happen. So for example, between 1 and 2, the variation gets less. So as we would expect, the control limits tighten up. Okay? Same thing down here with the moving range. So I think it's really, really great for teaching. Okay. Now I'm going to go back to the control chart options, and this time I'm going to pick an X bar chart. Okay. Now, if you notice, we have this variable day, and so if you see it, you'll notice, for example, there's a set of measurements on day 1, and then there's a set of measurements on day 2, day 3, day 4, and so on. Well, this is a nice data set that might make sense to do an X bar chart where we're going to use day as that subgroup, and we might want, say, a mean and a range, or a mean and a standard deviation for calculated for each of those days and displayed on a control chart. So the way you do this in JUMP is I'm going to put in the diameter here, and I'm going to do sample label day. And again, I can change options. Maybe I want to see a standard deviations chart or a range chart, and hit OK. And there is my mean and range chart for that data set where the subgroup is day. And of course, you can see them labeled down. Now, you might have noticed this. I've been dragging around graphs. So this is something you can do all across JUMP, is when you get a piece of output, you can sort of take your cursor and move around the graph to make it bigger or larger. And you can also sort of, by just dragging, you can actually start changing the scaling that you do here, or moving this around like this, right? So you don't actually have to go in and define the min and the max numerically. You can actually use this hand cursor and actually move it around yourself. And again, you drop down the red triangle, and there's going to be things related to an X bar chart and things that you can do related to an R chart. Again, some of those things are cosmetic. Some of those things are truly about analyses. Right? Now, if you looked under this control chart menu, you probably saw many other control charts. Right? So there's a set of control charts where we would look at attribute data like proportions and counts. Right? Then we have other range charts that are used for detecting small shifts. So I'm not going to go through them all. You can see the list here. So these are the standard charts that, one, you would see in practice, but two, would be typical in a 1 or 2 semester quality control course. Now, I mentioned there's another way to make control charts, and that is up here through the control chart builder. So I'm going to launch that, and what you get here, this is very similar to the graph builder in JUMP, where you get this blank canvas sitting there, and then you just start dragging in variables into the different roles. And this is nice because JUMP is going to recognize certain things. It's going to recognize a continuous variable from a categorical or count variable or binary variable, and then it's going to know that chart that would make sense for that data. So notice, I bring a continuous variable and I just drag it over and I drop it into the Y, and there you go. We've got diameter, we've got a moving range chart. It's making an individual moving range chart. If I wanted to grab phase, I could put phase up here, and I get that same graph that I was showing you earlier. So you may find using this control chart builder platform easier or better for illustrative purposes in classroom than just picking the chart. Because what's nice is you can drag these things on and off. So let me grab that again. And I can pull phase out, I can pull phase in. So look at this is great for teaching, right? Because you're trying to show things that are changing, and you could sort of bounce back and forth to some concept you're trying to teach. Okay, I'm going to close this, and I'm actually going to go back to the distribution platform, because I promised you I was going to show you tolerance intervals and prediction intervals. So I'm going to bring that diameter variable and just sort of do that distribution analysis again. And if you remember when we did this, under this red triangle is where I selected capability analysis. And again, it gave a sort of a brief capability analysis, and shortly I'm going to show you the platform that does that. We'll have a little bit more options. But there's two other analyses that can be done right from this distribution analysis that are very common in the quality world: prediction interval and tolerance intervals. Sometimes they don't get a lot of coverage in the classroom environment, but they really should, because they're used tremendously out in industry. So What a prediction interval does, and oh, you might notice this. This is common in all sorts of places in JUMP. When you float your cursor over a particular option, a little set of text is going to pop up to tell you what that tool is for. So you see a prediction interval is to predict some future observations. So I'm going to launch that. And so what you get to do is, with a certain level of confidence, I'm going to try to predict where a certain number of future observations will lie. So 1 is sort of the default, because that might be where I might say, hey, if a customer gets this product, this item, that's all the customer really cares about. They don't really care about all the items you make. They care about their one they get. I might want to estimate what could that experience be for just that one observation. And I'm going to hit OK. And right over here to the right, I get a prediction interval. So this is a lower and upper bound at the 95% confidence level of where a future observation will be. So if I just went and selected one item from the process that this data is representing, I'm 95% confident that it will land in that range. And again, this is a common thing done out in practice, though it doesn't get as much coverage as I think it should in stat courses and quality control courses. But again, it's very, very popular out in industry. Now again, as I was illustrating, if I want to collapse things because I just want to keep the screen clean, I can sort of do that. Now the other one I want to do is a tolerance interval. And again, this one is very, very popular out in quality applications. Quality engineers have to do this all the time. It's similar to capability analysis in the sense that you're trying to estimate where a distribution is relative to specs, but instead of defining the specs and trying to estimate the percentage of a distribution within those specs or outside of those specs, you're not defining the specs, you're defining the proportion of the distribution, and you want to come back and say, what values capture that proportion? So it's almost like the opposite of the capability question. Capability, you define the specs and estimate the proportion. Tolerance intervals, you define the proportion and you're estimating those values. So you can specify the proportion of the distribution I want to cover. So the default is 90%. And the confidence level that I want this interval based on. So this is a little tricky because you got sort of two percentages going on, but I'm going to estimate with 95% confidence where 90% of the distribution lies. And you can pick to use a normal distribution or non-parametric, but from looking at this data, we saw that the normal distribution was very appropriate, so we'll keep it there. Click OK, and then added to my output over here is a tolerance interval. And so the way you interpret these two numbers there is you say I'm 95% confident that 90% of the distribution is going to lie between 3.77 and 4.91, rounding off there. Okay. So, and if I add, of course, we'll add this to capability analysis just to put this on here all together. Okay. And these all together, sort of a distribution summary, a prediction interval, and a tolerance interval, and a capability analysis, those go together a lot. I think, not just do they go together in practice. I'm going to just change the display here. If you notice, I can choose to have this output going across horizontally or vertically. And you'll see that in a lot of places in JUMP. You'll see this little stack under the main red triangle up here. And so I can put, so all these together, I think being taught together is really, really nice because they're similar, but they're answering slightly different questions. And again, in practice, they're used together quite a bit. Okay, so now let me show you the capability analysis from the process capability platform. Okay. So I'm going to open the process capability platform. I'm going to slide in diameter into the role of my variable. Now, if I do this, it's not going to take into account that I have measurements on different days, but maybe I want to do that, right? Because there's the difference between the CP, CPK metrics and the PP and the PPK metrics. And so if I do this, I'm just going to get the overall capability, but I might want that subgroup capability in there as well. And so this is really neat. The way you do it is I'm going to open up this little process subgrouping. I grab day, which is that subgroup variable, and I'm going to also click on nest. And then basically I'm going to hit this button that says nest that subgroup column with diameter. So now you'll see it's labeled as day is that subgroup nested within diameter. And again, I got a bunch of different options I can do here. I'm going to close this up. For example, I can put in a historic standard deviation, so all the control limits are based on that versus the data that we're analyzing. Same thing, I can choose different distributions here to select from, but I will leave it as the default. And I'm going to hit OK. And I got to type in the specification limits. All right. And so this is giving a little bit more information than we saw when we ran capability in the distribution platform. So this is nice. We've got the overall and the within normal distribution curves drawn over. We'll see those estimates from overall or within, because I put in that subgroup. We got the proportion out of spec, CPK, all those classic metrics that you're going to see. And again, just like everything else, I go in here, I'm going to have options to what to show, what to display. Same thing here. So use that, take advantage of that red triangle. Now this is a really great thing that I love, and you can do this all over JMP. When you run an analysis, you'll see this tool under the main red triangle called the local data filter. And what that allows you to do is I can start excluding or including certain groups of data and watch all the output change. So for example, you notice we have different machines and different operators. So I'm going to click on machine, and I'm going to hit this little add button. And you notice I've got 3 different machines here. There's this A386, there's this A455, and there's this C334. Just 3 different machines. Well, I can click between these because whether I want to include one or maybe I want to include 2 or all 3. And as I'm doing this, notice in real time, all of these capability metrics and the graphs are changing. So not only is this great for analyzing, but it's awesome for teaching because that's what you want to show. We want to say, hey, which machine has the best capability? And if you set up that data the way you want for teaching purposes, where you can show, hey, maybe one machine has excessive variability, but it's on target. Maybe another machine has low variability, but it's off target. And for teaching and for the students playing around with the data, this local data filter is a great platform to do that. And in fact, I'm going to just show you what else you can do with this is I can filter by any variable. So maybe I want to filter by day, by machine, phase, and if I had continuous variables, I can even filter by that, and maybe I want to look at it under certain conditions. Now I have only the one continuous variable here, so no, I'm not going to do that, but if I had another continuous variable, I could even filter by that within some range. So this local data filter is a really great tool, and you can do this pretty much in every platform and JMP. So it's great for analysis, but I think it's awesome for teaching because that's the best way to compare and contrast as you change things. Okay, I'm going to close this up, and actually I'm going to close this file because we're going to move to a different data set. Okay. So in this data set, I've got a set of processes I'm studying. So you can see this process 1, 2, 3, all the way to process 7, okay? Now, in this case, I may want to do sort of individual capability analyses, but I want to compare them. Now, I'm going to show you a little something here that if I go under this column, and I'm going to show you column info, you'll notice that underneath that column, underneath that variable process 1, I have the lower target and upper spec already defined. Okay, and same thing with all of these. So I'm just going to go under another one, process 3, lower spec, target, upper spec, and notice they're different. So each of these processes has a unique set of lower and upper spec limits. Well, the fact that that information is saved in there when I run a capability analysis, I don't have to tell JMP what those specs are because those variables have that information already saved. If you remember from the example I just showed you, I had to type in those numbers. But I don't have to because I've got that information saved already. Okay, so now when I go and do a capability analysis, I'm going to put in all the variables here. And I'm not going to deal with any kind of subgrouping or anything. I'm going to hit OK. And hold on, I'm just going to drag this up. Okay. So what I'm going to get here is for each of those processes, I'm going to get a capability analysis. So here's process 1, there's process 2, process 3, process 4, and so on. And of course, they're all made relative to their specific set of specification limits. That first one is 3, 10, and 25. For process 2, it's 10.5, 12.5, 14.5. So that's really great because you can run a whole collection of capability analyses with all of that information saved, so you don't have to be manually typing it in. In fact, if you had a whole bunch of variables, say more than just 7, well, you can do it for 7, but this is more convenient when you have more, I can actually create a data table of all of those spec limits displayed like this, and I can actually just upload them into JMP, and JMP's going to attach those spec limits to each one of those variables. So this is really nice if you have a lot of variables because you can just sort of bring in that file that might have all that content already in it. So again, this looks just like what I did for doing just one variable, but now I'm going to have all the output for all of them. Now, as you scroll through here, you may start to detect things like, here's process 4, for example. You might look at this histogram and that normal distribution displayed over that and say, doesn't quite seem right. That maybe looks like a different distribution. Well, you can actually do different distributions if you want. So underneath the red triangle for this process 4 capability analysis, I can say compare distributions. And now you see right here, I've got the graphic, the histogram with the spec limits and the normal distribution drawn over it because it's the one selected. But I can start looking at maybe other distributions. So here's the log normal. So that purple line is the log normal distribution fit to that data. Looks a lot better. And down here, I can see some measures of fit for that. And then if I hit select for log normal, now all the output down here, I'm going to scroll down a little bit so you can see it. So now all the output for the capability analysis for process 4 is now based upon the log normal distribution, not the normal distribution. And then I can switch it back to normal. And again, I can compare more than just 2 if I want. I'm going to throw in the Y bowl. Maybe I even want to illustrate sort of non-parametric analyses, exponential, and so on. So again, it's great to analyze, but this is another example where I think JMP is great in the classroom because that's kind of what you want to do when you're teaching, right? You want to say, hey, watch how the capability metrics change when I pick a more appropriate distribution and see how that's going to estimate the in-spec, out-of-spec. And I think that's great what we can do with teaching. And I love that you can do this in the moment. You don't have to go back and run a separate analysis for log normal, then run a separate one for Y-able, and click back and forth to see which, how that changes. You can do it right from the output, right from this analysis output. You can click around, which I really like doing that. Now, if you're teaching how to evaluate what the right distribution is, well, right under that red triangle, I can actually make some probability plots. Okay, so here's a probability plot of the data fit to a normal distribution, and we can see it's not a great fit. Okay, I get some options of what I'm going to display for the confidence bands. Okay, and again, let me get back up to the compared distribution. Then we go to the log normal. Hold on one moment here. Switch off the normal. Okay, so now I've got the log normal, and that you can illustrate. Oh, notice the data fits that distribution much better. Well, that distribution fits that data much better, and so this would be a more appropriate distribution to interpret the output. And here's all the capability metrics for that. Again, I think it's great for analysis, but I think it's really great for teaching because you can click back and forth between different distributions. and watch how all those results change. Now, just like I've shown you before, I can sort of collapse all these individual reports if I want. But really what I want to show you, well, I'm just going to collapse a couple of these. I want to clean up my screen a little bit too. So I'm just going to collapse all those individual reports. Now I'm going to open up this thing called the goal plot. Now, what this does is it's going to display the results of each of those variables, right? There's 7 of them. Remember, we have process 1 through 7. And it's making this really neat graph, which is putting a sort of a standard deviation. Now, it's standardized to specs because obviously we have different specs for every one of these variables, and they're on different scales. Like if you look at, process 6, you can see the scale that data is on, and process 7, the scale that's data on. So to look at a graph, we really need to standardize it. So on the y-axis, you have a measure of variability, and then on the x-axis, you have the mean shifted away from, again, the mean measured relative to those specs. So if it's right on the center versus closer to the lower upper spec, it's going to be plotted accordingly. Now, this is really nice because this is where I can do that comparison of all 7 different capability analysis together. And this zone that you see here, this little red, actually I'm going to add a little shade that actually. This triangle zone here is based upon a PPK of 1, and I can move that around if I want. And so if I want to see a higher process capability, let's say I'm going to make it 2, PPK of 2. And so this red triangle is based upon a PPK value of 2. And then I can look at how these values compare to that capability. Now, you're plotting 2 dimensions. Remember, the variability and the mean. So I can look at things like, for example, this is process 1. It's right on target. It's sort of right in the center of those spec limits. However, its variation is so large that it doesn't have a desirable capability. In fact, it's quite bad. So over here, say process 5, I got process 6, process 3. Those are all distributions that are shifted towards the lower spec. So they're not centered right between the spec limits, but they're shifted to the lower spec. Now, they have a lot lower variation than process 1, but because of that shift and, of course, the amount of variation, they don't have a PPK value lower than 2. Now, I can kind of slide this thing around and kind of see, where they kind of cross that line to sort of get a, quick little ballpark of that capability. And these 2 are interesting here. So this one is process 7. So another one that's right on target, just like process 1, but its variation is small enough that it lands inside of that range of having a PPK value of greater than 2. And then this one's interesting here, process 2. It has, in fact, the lowest amount of variation in all of these 7 processes. Okay. However, because it's shifted off of target and it's closer to the upper spec limit, it just lands right outside of that capability value of 2. So as I keep on saying, where I think JUMP is great is not only is it a great tool to be out in practice because it helps make analyses easier, but things like this I think make teaching really great because you can do that classic contrast and compare. And I think it's when students can contrast and compare many things and watch how the results change under different situations. That's where I really think the learning happens. Okay, now I'm going to close up that goal plot. There's some other graphs here that are nice to look at. So here's a similar approach of looking at standardized values of the data in box plots relative to the spec limits. And all of it is standardized. So I'm viewing the spec limits all on the same scale, even though originally they're not. So it allows for a good comparison. So, process 1, remember, is right on target, but it has the largest amount of variation, right? We saw that. And I'm going to open up the goal plot again so you can look at them together, right? So there's process 1 up there on target, but high amount of variation, right? So here's process 6, right? Very low variation, as you can see. However, it's outside of the lower spec limit, so that's why the capability isn't good. Here's process 2, low variation, but it's close to the upper spec limit, so it's just getting to the point where the capability isn't above 2. And that last one here, that's process 7, very close to target, and the variation is low, and so that one has the best capability. Okay. All right, I'm going to close this one up here. Now, something else you can do here when you've got multiple variables is you can think of capability in the sense of looking at many variables together. And we sort of did that in the previous analysis I just did, but it's common that you want to think, well, how does this all behave together? So I'm going to do this for some the multivariate chart. How this behaves over time, but not in a one-dimensional sense, but in all 7 dimensions. And so here is what's called the t-square chart. And so what this is doing is it's only looking at one dimension here for the graph, but this distance plotted on the y-axis is how far each of those points are from the center in a multidimensional sense. So this is a way to look at the stability of a process over time, but with all 7 variables. And if you're unfamiliar with this, I'm just going to do a quick little thing here just to illustrate sort of what's going on. And I'm going to do it by just grabbing 3 variables because it'll be kind of easier to illustrate with 3. So let's just say process variable 1, 2, and 3, and here's some scatter plots of them. And I'm going to pull up here. Let's do, I can shade these up. Hold on one second. I'm going to pull up a 3D scatter plot of those 3 variables with an ellipse on them. So basically what's going on in this t-squared multivariate control chart is it's plotting essentially the distance from the center of that ellipsoid there to those points. So you can see how some of those points are outside of that shaded region. Those are corresponding to these points outside of that upper control limit. So it's like that upper control limit is basically the edge of that ellipsoid. So I don't know if it's a topic you're teaching in your classes quite yet, but again, out in the real world, most data is multidimensional, and engineers and scientists want to look at it that way. So if you're not teaching this topic yet, this is a really good one to add to your curriculum. Okay. I'm going to close this up because we're going to move on to a different example. Okay. So this is an example that's going to illustrate running a measurement systems analysis, sort of like a gauge R&R study. So for those of you not familiar with the gauge R&R study, this is where you have, say, different operators. You can have things beyond operators, but that's a common one. You can have different operators measuring different parts multiple times. And so you'll see, for example, those first two rows are operator A measuring part 1 twice, and then so on. Operator A measuring part 2 twice, and part 3 so on. And then we have operator B, same thing, part 1 twice, part 2 twice, etc. And all the way to operator C for a total of 30 measurement values that we have here displayed in column Y. Okay. So a typical problem that's done out in industry is, hey, well, we should evaluate the variation in using this measurement system. How do things change when different operators make measurements on different parts? Okay. So I'm going to go under the quality and process platform. And there's 2 techniques that JUMP has to do this. And there's some similar information between the 2, but they're designed to give slightly different information. The order of the output is a little bit different. So you might find one easier to use than the other. But again, you can get very similar information from both of them. So I'm going to open up this one called the variability chart. Okay. Now my response variable is y, so I'm going to drag that over. Okay. And I'm going to put in part. So I've got a little role for part. And I've got a grouping variable, which in this case is going to be operator. Now, it can be other things. Maybe it's not operator. Maybe you're measuring location on the part, or maybe there's different settings on the measurement system. So you don't have to just be operator here, even though that's kind of one of the most common ones. And so I'm going to throw in operator. Okay. And so, and this is very common across all of JUMP. Sometimes the first piece of output you're going to get is just a graphical display. So it's nice in teaching because before you get to some of the more advanced concepts, you can start off with, hey, let's just look at the data visually. Let's look at it graphically, because you can tell a lot of information from that anyway, but it allows you to kind of unfold the analysis instead of getting all the output all right away. And then as you're teaching, you can kind of keep on showing more options. So this is a quick way to say, okay, I've got 3 different operators. They're measuring 5 different parts twice, and there's all my data, right? And down here, I'm looking at the variability between those 2 measurements, and I can, again, see that across the 5 parts within the 3 operators, and then a whole bunch of options under here, okay? So, for example, I can add some information to the graph. So here I just added the overall mean of all the data, or I can add the group mean. So that purple line is just the mean of operator A's measurements, the mean of operator B's measurements, and the mean of operator C measurements. Okay, you can see quite a bit of things I can do here. I can show the variance components. I can actually show the classic output from a gauge R&R study. So I'm going to do that. Okay, and again, I can pick, am I doing cross-nested? And for those unfamiliar with that, that's kind of the distinction often used if you're doing destructive testing and the same part can't be measured multiple times, but we'll leave it as the default. Okay. And I have information I can do here. I don't need all of this, but I can put in things like spec limits, tolerance widths, so that more output gets displayed evaluating this measurement system relative to those. But I'm just going to keep the output a little simple for now and leave it just with the default. I'm going to just move the screen a little bit so you can see. So now what gets added is a whole bunch of the numerical pieces of output that correspond to a classic gauge R&R study, right? The repeatability, the reproducibility, the total variation, and then I can see those variance components displayed here. So again, this is really nice for teaching because maybe it's an intro class and you just want to start with the graphical displays, get them used to that, get them to explore variation that way, and then when you're ready to start doing more of the formal statistical analyses, you can start displaying things like variance components and ANOVA tables, testing, and all the more advanced stat. But I like this approach because I said you can keep it simple if you want, or expand if that makes sense. All right. I'm going to close that guy up. And I'm going to look at another common measurement system study that's done, which is this thing called an attribute measurement study. So this is where you have different parts. So I got a variable here, part. So you see these first 3 are part 1, okay? And I got all the way down to part 50. So each part, as you can see, is looked at 3 times, and it's looked at by 3 different operators. So I've got operator A, B, and C. And this data is binary. So let's say this part is either conforming or non-conforming, and the purpose of the study is to have an operator or an appraiser look at the part and classify it as such. Okay. So for these first 3 observations of the data table, I've got part 1 examined 3 times by 3 different operators and the true state of nature of that part. And I'll say 1 is acceptable and 0 is not acceptable, or conforming and non-conforming. So part number 1 is truly conforming. It is a good part. Of course, the appraisers don't know that. That's the whole purpose of doing the study. And when you do this, you'll see that operator A when they looked at it 3 separate times, each time they correctly said, yes, that part is conforming, and operator B, the same thing, and operator C, the same thing. So of those 9 measurements made by those 3 operators 3 times, they got it correct every single time. They all said it was conforming every time they looked at it, and that part was truly conforming. And you can sort of go down and see where they're agreeing and where they're not. And so I'm just going to scroll to a place where there isn't 100% agreement, and you can see that here. So part number 6, which is truly a good part, you can see 1, 1, 1. When operator A looked at it, the first and second time they thought it was a good part, but the third time they didn't think it was a good part. Now remember, the operator doesn't know they're looking at the same part multiple times. You know, you do this study as a blind study where they don't know. Operator B, same thing, measured 2 of the times, thought it was a good part, 1 of the times they thought it was a bad part. And operator C got it right once and wrong twice. Okay, so this is a classic study done out in industry to evaluate how people can appraise things. So I'm going to show you where that analysis is. Okay. So I'm going to open up that variability attribute chart. Okay, so I'm going to put the 3 operators here as the response, because that's those columns A, B, and C. Those are the responses. The 1s and 0s are the yeses and nos. The standard, the true state of nature of those parts, I'm going to put here in the standard. And then, of course, I have to put in the part so they can see that there's 50 different parts there. And hit OK. Now notice, you know, JUMP has attribute as the default selected because we put in binary data, so it knows that. When we did the continuous one, the default was set to variability, so we don't even have to change anything there. JUMP recognizes it. Okay. And again, like a classic thing in JUMP is it starts off with a little graphical display. So what you're looking at here is all the 50 parts and the percentage of agreement. So remember, parts 1 through 5, they got it right every time, the 3 operators under the 3 measurements, so you have 100% agreement. Part 6, when I showed you that, you remember, is part 6, there was some disagreement. You don't have 100% agreement, and so it's plotting that. So again, you can keep this analysis really simple and just sort of look at that percent agreement or not. This next graph right down here is showing what that percent agreement is for the raters across all the 50 parts they looked at in 3 measurements. And then there's all sorts of other metrics down here which start getting into evaluating what percentage of the time do they get it right. You may be teaching the metric CAPA, which is used in attribute agreement analysis to sort of to measure that agreement. But you've got percentages, confidence intervals for those percentages. You can look at which parts are misclassified. Is it that they get the non-conforming parts more wrong, or did they get the conforming parts more wrong? So all sorts of things you can do here. And again, I love this thing in JUMP is you can start just collapsing different pieces. So if you're demonstrating this in class, you don't have to have the students see everything at once. You can just have them focus on specific pieces of output and then collapse that if you don't want to focus on that. Okay. Now, we only have a few minutes left, so we don't really have an opportunity to show the Design of Experiments platform. However, we have lots of other webinars that focus just on that. Not only that are up and coming, but if you go to our webinar library, you can watch some webinars on Design of Experiments. So apologize I didn't get to it. I just wanted to mention that we may have a chance to get to it in this session. But we didn't. So with a few minutes we have left, why don't we open it up to some questions?
Hi, Kevin. This is Pawnee. We don't really have any questions right now, so if there's anything else that you would like to expand on, we still have a few minutes left to do that.
Perfect. I will do that. Actually, I had something in mind that I wanted to show. Okay. So one is there's, for those of you who are using the Doug Montgomery's Intro to Quality Control book, which you may very well be, it's one of the more popular books to use in the classroom. So we just came out with a JUMP companion to that. So this is a great supplement to that book where this is going to focus on how to run all of those analyses in JUMP. Okay, so it's more a cookbook of running the analyses, and of course it's teaching concepts in there as well, but the textbook is more for that. This is the companion that goes with it. So this is great for your students to have, because then your students don't have to keep on bugging you for how to do these analyses in JUMP. They've got a great resource, so they can go to each of those chapters. It's synced right up with the book, so you can go to that chapter and say, okay, now how do I make all those control charts, or how do I run all those analyses I am learning in the course. And then I'm pointing out two others here that really focus on quality Six Sigma applications. This Visual Six Sigma book, this is one of the authors in this book is actually one of the folks on my team, one of my colleagues. And then we have this book that's focusing on quality for pharmaceutical. Sorry, that's a little blurry. I made that much larger than I should have. If you go to jump.com/teach, you will see that you can look up all these resources, books that use JUMP, the learning library to get other webinars and case studies, sample data sets, but you can find a list of those books there. We can go in order. But the other thing that's super exciting, and this is just launched recently, we're developing a online course on the statistical techniques that are common in the engineering industrial world, right? So the classic quality problems. Now, of course, it's gonna cover all the standard, statistical inference, like t-test and ANOVA and regression, but it has sections on quality control. So this is an ability to sort of have an online supplement to what you might be teaching that your students can participate in, or you yourself can participate in it and get your kind of finger on the pulse of what's going on out there in industry. This is made by folks who have a tremendous amount of industry experience, and so they know those statistical tools that industry is expecting students to know. They're expecting their quality engineers and scientists to know. So if you go to jump.com, you can look this up and see that we've got this really exciting online course that is in development, and we're releasing chapter by chapter as it gets developed. And actually, while we're waiting for questions, if there is any, I will just show you that part of the website I was mentioning. So if you go to jump.com teach, you're going to get to the academic section of the JUMP website, and here you're going to find a tremendous amount of resources. And this is great to point your students to, because again, you're there to teach concepts. You're there to help explain, how these analyses are used, what they're used for, the power of them, maybe even the background theory to them. But you don't want to spend your class time showing them how to use JUMP. And we have all these resources for that. So we got the webinars, we got a library of webinars, we've got this learning library, which has all these one-page guides and short little videos on specific topics. So here's quality and process. So I can go here, and here are all these videos, quick little videos on how to run each of those analyses. Now, they're not meant to teach the concepts, they're more just meant to run it. So I'm going to, for example, open up this one-page guide, and so here's just this really step-by-step instructions of how do you say make that control chart or whatever the analysis is. And so these are great to supply to your students. So again, they don't have to get stuck and bother you about how they run analysis. You can just point them to all those resources. And then, of course, in addition to that, course material library. This is where you find the books that are using JUMP. So those ones I just pointed out to you. Some interactive teaching tools, a case study library. So if you're looking for problem sets to give your students, we have a whole collection of problems by different types of courses, by analysis types. And we've got these great data sets. So these could be homework assignments or projects or tools you can give them in the lab. Okay. All right, so I'm just going to put up the screen again with my information. So if you have any questions, feel free to follow up with me. Here's my email address right here, and I'll be able to get the answers to your questions.
Thanks, Kevin, for the presentation.
Oh, thank you.
As Kevin mentioned, he provided his email address to touch base with him if you have any further questions. Thank you for joining us for today's webcast, and enjoy the rest of your day.
Thanks, Bonnie. Thanks, everyone.